Welcome back to the Explainer, everyone. Okay, today we're tackling a seriously high-stakes concept that literally sits at the very foundation of predictive data. We're talking about rigorously interrogating a statistical model before you can ever actually trust it. You see, building a predictive model, it isn't just about tossing some data into a computer and blindly accepting whatever line it spits out. It's a full-on investigation. Really, it's an interrogation. If you are building models that impact businesses, science, or, actual human lives, you absolutely need certainty that your model is telling you the truth.
So is your regression line lying to you? Okay, let's dive into this. I know it is incredibly tempting to just map your data points, hit run on your software, and boom, find that simple line of best fit. But listen, finding a line just isn't enough. We actually have to prove it's valid. Just because a mathematical line can be drawn through a scatterplot doesn't mean that line is honest or even useful. A model isn't finished just because you found a line. If there are hidden biases or structural flaws lurking in your data, well, that beautiful line might be quietly lying right to your face.
Here is the clear roadmap for our interrogation. We'll start with 1, the setup, move to 2, linearity, 3, normality, 4, homoscedasticity, 5, multicollinearity, and finally, 6, final results.
All right, Section 1, the setup. Meet the suspect.
We're bringing our model right into the interrogation room. Now, before we can grill the suspect, we need to know exactly what they're claiming to do, right? Our suspect today is a model working with the classic MPG dataset. Its claim? That it can accurately predict fuel efficiency, miles per gallon, by looking at 3 specific variables: the vehicle's horsepower, its overall weight, and its model year. That is our setup. And think about why this really matters for a second. If a huge auto manufacturer relies on this exact model to meet strict governmental fuel efficiency regulations, and the model is wrong, those predictions will be expensively wrong. We're talking millions of dollars potentially on the line. So let's see if this model actually holds up under pressure.
Moving to Section 2, linearity, checking the data's shape.
And this brilliantly illustrates our first test. When we plot the residuals, we want to see a random, structureless cloud. This is exactly what you want to see. A random, messy cloud means our model has successfully captured the main trends, and what's left over is literally just random noise. The model is innocent. It's a solid, good linear fit. But contrast that with a distinct, curved U-shape pattern. Now that is a massive red flag. If your errors form a shape like a U, the relationship is inherently nonlinear. The model is guilty, plain and simple, of trying to force a straight line onto curved data.
Next up, Section 3.
Normality, hunting for the bell curve.
So to confirm that our model's residuals actually form that perfect bell curve, we've got a couple of specific visual tools in our toolkit. First, we use histograms. These let us quickly visualize if the errors pile up neatly right in the middle and taper off symmetrically at the ends, giving us that classic bell shape. We also use QQ plots, which basically line up our actual data against a theoretical normal distribution. If the dots on the QQ plot hug a nice straight 45-degree diagonal line, well, we can breathe a huge sigh of relief. It means our errors are beautifully normally distributed.
Phase 2 of the interrogation, Section 4. Homoscedasticity, the threat of the fan shape.
I know, homoscedasticity sounds like a super intimidating statistical word, but it simply means an equal spread of errors across your entire dataset. That's it, equal error spread. When you look at your predictions from the lowest values all the way up to the highest values, you want the band of errors to remain relatively consistent in width. Honestly, it should look like a steady tube or a continuous tunnel of data points.
But we need to talk about an urgent warning here. We've got to contrast homoscedasticity with its evil twin, heteroscedasticity. When you have heteroscedasticity, your errors don't form that neat tube. Instead, they form a dreaded fan or cone shape. This means that as your predictions get larger, the errors get wildly wider and way more unpredictable. Why is this so incredibly dangerous? Because a fan shape in the data completely invalidates our crucial statistical tests. You literally can't trust your confidence intervals if your model gets progressively more confused as the numbers scale up.
Let's shift focus to Section 5, multicollinearity, redundant sabotage.
Now, what's really interesting about this slide is how we handle this internal investigation. We're actively looking for redundant variables that internally sabotage the model by basically just talking over each other. Think about it. If we're using both horsepower and engine size to predict MPG, those two variables might overlap so much that they actually confuse the model about which one is doing the heavy lifting. We define this internal sabotage using the variance inflation factor, or VIF. Look closely at the formula. VIF equals 1 divided by 1 minus r squared.
If a variable is highly redundant, it'll have a very high R² when compared to the other variables. And because of the way this math works, a high R² makes the denominator tiny, which causes the entire VIF score to absolutely explode. A high VIF mathematically proves that your redundant variables are fatally inflating the variance and ruining your model. We've got to strip those out for sure.
Finally, Section 6, Final Results, Reading the Verdict.
So the crucial point is right here on this OLS regression results table. Let me guide you through the two columns that matter the most to our final verdict. First up, the coefficient. This tells us the direction and the exact impact of each variable. For instance, horsepower and weight have negative coefficients, meaning as they go up, our miles per gallon go down, which, makes perfect sense. Heavy, powerful cars totally guzzle gas. Model year, on the other hand, is positive, meaning newer cars are more efficient. But check out the p-value column. We want these numbers to be tiny, typically under 0.05. And they are. They're all incredibly close to 0. This definitively proves the significance of our variables. They aren't just random flukes, they legitimately drive fuel efficiency.
And for the absolute final piece of the puzzle, our R² value, 0.814. Honestly, this is a triumph. An R² of 0.814 means that over 81% of the variance in a car's fuel efficiency is successfully explained by our specific mix of horsepower, weight, and model year. And because we've passed all those previous rigorous diagnostic checks, we can actually trust this high number. Our model has survived the interrogation, and it is highly reliable.
Let's quickly cement this whole rigorous process. If you want to master regression diagnostics, here is your definitive checklist. First, confirm linearity to avoid those U-shapes. Second, check normality with your QQ plots. Third, prove homoscedasticity by avoiding the dreaded fan shape. Fourth, remove multicollinearity using the VIF formula. And finally, step 5, read your OLS results to confirm your coefficients and your R². These checks guarantee that a model is actually reliable for real-world predictions.
We've seen today just how easy it is for a simple line to hide massive statistical flaws. It really makes you wonder, if this level of interrogation is required for a simple car model, what other unseen errors are hiding in the algorithms you interact with every single day? Whether it's financial projections, social media feeds, or medical risk calculators, remember, never just trust the line. Interrogate the model. Thanks for joining me on this explainer, and keep questioning the data.